Welcome to this walkthrough of LeetCode problem number 191, number of 1 bits. In this problem, we'll explore how to efficiently determine the Hamming weight, or the number of 1 bits, in a 32-bit unsigned integer. We'll review a variety of approaches and their trade-offs. Let's dive in. The problem is called number of 1 bits. Our goal is to write a function that takes an unsigned integer as input and returns the number of 1 bits present in its binary representation. This count of 1 bits is also known as the Hamming weight. For the input, we're working with a 32-bit binary string, where the number is represented in binary format. For example, an input like 000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000represents the number of 1 bits in the input string. To illustrate this, consider the example where the input is n equals 00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000ɔ In the example of n equals 000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 the binary string contains 3 1 bits, which appear at positions 1, 2, and 4 when counting from the rightmost bit. This is why the output for this input is 3. Now, let's look at another example, when the input is n equals 000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000w, which is located at position 8 from the right. As a result, the output here is 1. These examples show how the function calculates the number of 1 bits, regardless of where they are positioned in the binary string. Another example provides the input n equals 11111111111111111111111111101. This binary string contains 31 1 bits, and only 1 bit is a 0. Therefore, the output for this input is 31. Now, let's talk about some constraints. First, the input is always treated as an unsigned integer. This means that negative numbers are not part of the input space. Additionally, the binary string will always have a fixed length of 32 bits. The input values can range from 0, which is represented as 0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 For the smallest possible value, 0, there are no 1 bits, so the output is 0. For the largest possible value, 42949672995, all 32 bits are 1, so the output is 32. Let's also discuss a few edge cases. For an input of 0, which is represented as all zeros, the output is 0 because there are no 1 bits. On the other hand, for an input of 42949672995, which is represented as all ones, the output is 32 because all 32 bits are 1. Another interesting case is when the input is a power of 2, such as 16. In binary, this is represented as 0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 So the output in this case is 1. These scenarios highlight the importance of understanding the structure of the binary input and how the function calculates the number of 1 bits in various situations. To solve the problem of counting the number of 1 bits in a 32-bit unsigned integer, we explored several approaches, each with its own trade-offs. The first approach we considered is a brute force method using bit masking. The idea here is to examine each of the 32 bits in the binary representation, one at a time, to check if it is set to 1. This is achieved by using a bitwise AND operation between the number and a mask that isolates a single bit. For example, starting with a mask of 1, we can check if the least significant bit is 1. After each check, we shift the mask to the left to examine the next bit. By iterating through all 32 bits and counting how many times we find a 1, we can determine the Hamming weight. While this method is simple and ensures all bits are checked, it performs unnecessary work when encountering 0 bits, making it less efficient for sparse numbers where most bits are 0. A more optimized approach for this problem is Brian Kernighan's algorithm. This method eliminates the need to iterate through all 32 bits by focusing only on the 1 bits in the binary representation. The key insight here is that we can clear the least significant 1 bit in a number with the operation n equals n and n1. Each time we perform this operation, the total number of 1 bits in the number is reduced by 1. By repeatedly applying this operation while the number is non-zero, we count the total number of 1 bits in just as many iterations as there are ones. For instance, if the binary representation of the number is 110, the operation 110 and 101 results in 100, effectively removing the least significant 1. This approach is significantly faster for numbers with fewer 1 bits because it skips over all the 0 bits entirely, making it both efficient and elegant. Another approach we considered involves leveraging library functions or pre-computed lookup tables. Many programming languages, such as Python, offer built-in functions like bin, n, .count, 1, that directly count the 1 bits in the binary representation of a number. This is a concise and convenient method. Alternatively, we can use a pre-computed lookup table. By dividing the 32-bit number into 4 8-bit chunks, we can look up the Hamming weight of each byte in a table and sum up the results. The table itself would store the number of 1 bits for all possible 8-bit values, from 0 to 255. While the lookup table approach achieves constant time complexity due to its fixed size, it requires extra memory and pre-processing to create the table. These methods are fast and easy to implement, but library functions may not always be allowed in competitive programming, and lookup tables trade memory for speed. After evaluating the different approaches, we selected Brian Kernighan's algorithm as our solution. This method offers a great balance of efficiency, simplicity, and scalability. It minimizes the number of iterations to just the count of 1 bits, making it particularly fast for sparse numbers with few ones. Unlike the brute force approach, it avoids unnecessary checks for 0 bits, which saves time. While the algorithm requires a bit of understanding of bit-level operations, it is still straightforward and does not need additional memory, such as a lookup table. Compared to the other methods, it is both practical and efficient for solving this problem. While brute force is simpler to implement and lookup tables are faster for dense binary numbers, Brian Kernighan's algorithm stands out as the most well-rounded and optimal choice for this task. To summarize the final complexity of our chosen approach, Brian Kernighan's algorithm operates with a time complexity of O, k, where k is the number of 1 bits in the binary representation of the number. This makes it highly efficient for sparse numbers. Additionally, the space complexity is O, 1, as it does not require any additional memory apart from the counter and the variable storing the number. This combination of low time and space complexity makes it an ideal solution for counting 1 bits in a 32-bit unsigned integer. In this problem, our goal is to count the number of 1 bits in the binary representation of a 32-bit unsigned integer, which is also known as the Hamming weight. For example, if the binary representation of the number is 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 straightforward method is a brute force approach that systematically examines each of the 32 bits in the number. Let's break this approach down into steps. First, we initialize a counter, count, to 0. This variable will keep track of how many 1 bits we've encountered. Then, we use a loop to iterate 32 times, once for each bit in the binary representation. On each iteration, we isolate the rightmost bit of the number by performing a bitwise AND operation with 1, that is, NN1. If the result is 1, it means the least significant bit is set, so we increment the count by 1. After checking the rightmost bit, we discard it by right-shifting the number using the operator. This effectively moves all the bits one position to the right, bringing the next bit into the least significant position. We repeat this process for all 32 bits, ensuring every bit is checked systematically. When the loop completes, we simply return the value of count as the final result. This value represents the total number of 1 bits in the binary representation of the input number. Now, there are a few important insights about this approach. First, the use of bitwise operations like AND and rightshift is crucial for efficiently isolating and checking each bit without requiring additional memory. These operations are fast and directly manipulate the binary representation of the number. Second, the fact that the input is guaranteed to be a 32-bit unsigned integer simplifies the implementation. Since we know the length of the binary representation is fixed, we can use a loop that runs exactly 32 times without needing to handle variable length input. This also makes the algorithm highly predictable in terms of execution. Lastly, the efficiency of this method is worth noting. The algorithm runs in constant time, 32, which simplifies to 1, because the number of iterations is fixed. It also requires only 1 space, as we use a single counter variable and manipulate the input number in place. Additionally, the algorithm handles various edge cases seamlessly. For instance, if the input is 0, a number with no 1 bits, the counter will never increment, and the result will correctly be 0. On the other hand, if the input is the maximum 32-bit unsigned integer, which has all 32 bits set to 1, the loop will count all 32 bits, and the result will be exactly 32. This approach is robust enough to handle any arbitrary combination of 1 and 0 bits. Regardless of the pattern, each bit is treated independently, ensuring the correctness of the algorithm. Now, let's look at the Python implementation of this method. The function _wait takes the input n and initializes a counter variable, count, to 0. It then uses a for loop that runs 32 times. In each iteration, it checks the least significant bit using n and 1. If the result is 1, the count is increment. After that, the number is right-shifted using n equals 1, which prepares it for the next iteration by discarding the least significant bit. Once the loop completes, the function returns the value of count. As for the complexity analysis, the time complexity is 32, which simplifies to 1, because the loop always runs a fixed number of iterations. The space complexity is 1, since no additional data structures are required, and the input number is manipulated in place. This makes the approach both simple and efficient, ensuring correctness for all valid 32-bit unsigned integers. This implementation of the number of 1 bits problem uses bitwise operations to efficiently count the number of 1 bits in a 32-bit unsigned integer. The method _wait takes an integer n as input and returns the count of 1 bits in its binary representation. First, we initialize a variable count to 0. This variable will store the cumulative count of 1 bits as we process the binary representation of n. The key operation occurs within a while loop that runs as long as n is not 0. Inside the loop, we use the bitwise in operator, and, to check whether the least significant bit, rightmost bit, of n is 1. If it is, the result of n and 1 will be 1, and we increment count by 1. If the bit is 0, the result of n and 1 will be 0, and count remains unchanged. After processing the least significant bit, we right-shift the bits of n by 1 position using the right-shift operator. This effectively discards the least significant bit that we just processed and moves the next bit into position for evaluation. The process repeats until all bits have been processed, which happens when n becomes 0. Finally, we return the value of count, which contains the total number of 1 bits in the binary representation of the input integer. This approach is efficient, operating in 1 time complexity since the loop runs at most 32 iterations for a 32-bit integer. The space complexity is 1, as well, as no additional data structures are used. This is the Java implementation of LeetCode problem number 191, number of 1 bits. The logic mirrors the provided Python solution. The method _wait iterates through the bits of the input integer n, counting the number of ones by checking the least significant bit and applying an unsigned right shift. Key differences from Python include explicit type declarations and the use of 4 unsigned right shifts, ensuring correct behavior for Java's 32-bit integers. To solve the problem of counting the number of 1 bits in an integer, we can use a simple iterative approach. Let's begin with an example where the input n is 11, which is represented as 1011 in binary. First, we initialize 2 variables. Count is set to 0 to keep track of the number of 1 bits, and n retains its initial value of 11. In the first iteration, we check the least significant bit, or LSB, by performing n and 1. Here, the binary operation 10, 11 and 0001 evaluates to 1, which means the LSB is 1. We then increment the count by 1, making it 1, and right-shift-N to remove the LSB. This updates N to 101, which is 5 in decimal. In the second iteration, the same process is repeated. The LSB of 101 is checked, and since 0101 and 0001 equals 1, we increment the count again to 2. Right-shifting N gives us 10, or 2 in decimal. In the third iteration, we check the LSB of 10. This time, 0010 and 0001 equals 0, so the count remains unchanged at 2. We right-shift N once more, resulting in 1. Now, the process continues as we examine the next bit. In the fourth iteration, the LSB of 1 is checked. The operation 0001 and 0001 results in 1, so we increment the count to 3. After right-shifting N, it becomes 0, which means there are no more bits to process. At this point, the loop terminates, and the final value of count is 3. This is the output for the input 11. Now, let's move on to another example where N is 128, represented as 1000000 in binary. We start with the same initialization, count is set to 0, and N is 128. In the first iteration, we check the LSB of 1000000 using NN1. The result is 0, so count remains unchanged at 0. We then right-shift N, which updates it to 64, represented as 01000000 in binary. In the second through seventh iterations, similar steps are repeated. Each time, the LSB of N is checked, and since all the bits in these positions are 0, the count remains at 0 throughout. After each iteration, N is right-shifted, reducing its binary representation until it eventually becomes 1, represented as 00000001. In the eighth iteration, the LSB of 1 is checked. The operation 00000001 and 00000001 results in 1, so we increment the count to 1. After right-shifting N, it becomes 0. At this point, the loop terminates, and the final value of count is 1. This is the output for the input 128. Finally, consider the simplest case where N is 0, represented as 0 in binary. Here, we initialize count to 0 and proceed to check the termination condition. When the input N is 0, the loop does not execute at all because the condition for the loop requires N to be non-zero. Since no iterations occur, the count remains at its initial value of 0. This means the output for the input 0 is simply 0. With this, we've walked through several examples to demonstrate how the solution iteratively counts the number of 1 bits in a given integer by checking each bit and updating the count accordingly. This approach is efficient and works consistently for all valid inputs. To determine the time complexity of the Hamming weight function, we need to analyze the operations performed in relation to the input size. Here, the input N is a 32-bit unsigned integer. The function uses a while loop that continues as long as N is non-zero. Within each iteration, the least significant bit is checked using the expression NN1, and the value of N is right-shifted by 1 bit using N equals 1. Both of these are constant time operations. Additionally, an increment operation count plus equals 1 is also constant time. In the worst-case scenario, where all 32 bits of N are set to 1, the loop will execute exactly 32 iterations. Since the number of iterations is fixed at 32 and does not depend on the value of N, the overall time complexity of the function is O(1). This is a result of the fact that we are working with a fixed-width 32-bit integer, making the number of operations constant regardless of the input. Now, let's consider the space complexity of the Hamming weight function. The algorithm only uses a single integer variable, count, to keep track of the number of 1 bits. This variable requires constant space, or O(1). Moreover, the function does not rely on any additional data structures or recursive calls, so there is no extra memory allocation involved. This simplicity means the algorithm has a constant space requirement, O(1). For comparison, a naive or brute force approach might involve converting the integer N to its binary representation as a string, iterating through the string, and counting the number of ones. For example, using Python's built-in bin, function and count method, we could write a solution like this: return bin n.count 1. While this approach works, it introduces additional overhead that we'll examine further. In the naive approach, converting n to its binary representation using bin n has a time complexity of O, b, where b is the number of bits in the input n. For a 32-bit integer, this means the process takes O, 32. Similarly, counting the ones in the resulting binary string also takes O, b, or O, 32. The space complexity here is O, b, as well, because the binary representation of n is stored as a string, which requires memory proportional to the number of bits. In contrast, the bitwise solution avoids this overhead entirely. It operates directly on the integer without string conversion, achieving constant time and space complexity, O1. When analyzing the best, average, and worst-case scenarios for the bitwise solution, the time complexity remains O1 in all cases because the loop depends solely on the fixed width of the 32-bit integer, not on the specific value of n. Finally, from a mathematical perspective, the number of iterations in the while loop is bounded by the number of bits in n, which is always 32 for a 32-bit integer. Since this is a constant, the asymptotic time complexity does not grow with the input size, confirming it as O1. Similarly, the space complexity remains O1, because the algorithm only uses a fixed number of variables. When working with bit manipulation, there are a few common mistakes to be mindful of. First, not handling leading zeros in unsigned integers is an issue that arises when assuming only the visible 1 bits in the decimal representation matter. For example, a 32-bit integer like 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 Another mistake is using floating point arithmetic, such as division by 2 or logarithmic operations, to count bits. These approaches introduce precision issues and are fundamentally incompatible with the integer-only nature of bit-level operations. Lastly, infinite loops can occur in shift-based approaches if the number isn't updated correctly during write shifts. For instance, if you have a condition like n greater than 0 but fail to reduce n properly with n equals n1, the loop will never terminate. It's critical to ensure that the number is consistently progressing towards 0 in such implementations. Another frequent error is using incorrect masking in bit manipulation. For example, using n0x0f instead of n1 to isolate a specific bit can lead to false positives or missed bits, which affects the accuracy of the count. Similarly, inefficiently iterating over all 32 bits in a number, even when there are only a few set bits, is suboptimal. For sparse numbers, this approach wastes computational effort and doesn't leverage early stopping techniques. From an interview perspective, it's important to recognize patterns in bit manipulation problems. Techniques like isolating the least significant bit with n and 1 or clearing it with n and n1 are fundamental skills to master. Additionally, optimizing for sparse inputs by using n and n1 can significantly reduce the number of iterations compared to looping over all 32 bits. Finally, always test edge cases such as 0, no set bits, 2-31 1, all bits set, and 1, only one set bit. If asked to compare methods, focus on trade-offs like the constant time complexity of looping through 32 bits versus the adaptive performance of approaches like n and n1 that scale with the number of set bits. This problem connects to several related problems that extend your understanding of bit manipulation. For example, LeetCode 338, Counting Bits, explores a dynamic programming approach to count bits, while LeetCode 461, Hamming Distance, calculates the Hamming weight of XOR results. Another example, LeetCode 476, Number Complement, involves flipping bits to find complements. Each of these problems builds on the techniques you're learning here. Now, when it comes to alternative approaches, one common method is the bit-by-bit check. This involves isolating the least significant bit using n and 1, then shifting the number right with n equals n1 to process the next bit. While simple and straightforward, this approach iterates over all 32 bits regardless of how many are set. A more efficient option for sparse numbers is Brian Kernighan's algorithm, which uses the operation n equals n and n1 to clear the least significant bit in each iteration. This drastically reduces the number of iterations, as it only processes the number of set bits, making it faster for numbers with sparse ones. In addition to these methods, there are other efficient approaches worth considering. One such approach is the use of a lookup table. By pre-computing the Hamming weights for all 8-bit numbers, from 0 to 255, you can process numbers in chunks of 8 bits at a time. This significantly speeds up the computation for repeated inputs, though it does require some additional space for the table. Another convenient option is leveraging built-in functions provided by many programming languages. For example, in Python, you can use bin n.count 1, while in C++, the __built-in _popcount n function achieves the same result. These built-in methods are highly optimized and concise, but they might not be allowed in coding interviews because they bypass the underlying logic. When practicing, focus on understanding the manual implementation to ensure you're prepared for scenarios where these shortcuts aren't available. Thank you for following along. Today, we explored different methods to solve the number of 1 bits problem, highlighting the importance of bit manipulation in coding. Remember, practice is key to mastering these concepts. If you enjoyed this walkthrough, please like and subscribe for more algorithm insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!